What's up, everybody? It is great to see y'all again. We are on the 2024 FRQ number 5 for Calc AB. Super excited. We're getting closer to the end of this year, if you've been kind of tracking along one by one. So today, we are going to be looking at this curve, and it looks like we're going to be dealing with a differential equation for a lot of this question. I'm a big fan of differential equations. You can actually take classes in college specifically devoted to differential equations, ones that are a little bit more simple like this, but there are also these things called partial differential equations that become their own huge separate mess. So if you're really interested in math, differential equations, there is like so much opportunity to keep going, keep learning more about this, which is part of what makes this really exciting for me. So let's look at this question together. Dive right in. So question 5 says, consider the curve defined by the equation x squared plus 3y plus 2y squared equals 48. And it can be shown that dy dx, or our derivative of y with respect to x, equals negative 2x over 3 plus 4y. Okay, so we got a curve and a differential, which I would say sometimes is uncommon. Most of the time, questions will only give us one or the other, so kind of them that they would give us both, honestly. But we can look at part A. So, part A says there's a point on the curve near 2 comma 4 with x coordinate of 3. And it says use the tangent to the curve at 2 comma 4 to approximate the y coordinate of this point. So we have the curve, right? If we wanted to find the y value, I could just plug in x equals 3 and solve for y, and that would give us the exact value. But they're asking us to approximate using a tangent line approximation. So let's find the tangent line. We know that a tangent line is represented by y minus y naught is equal to my slope times x minus x naught, right? That's my point slope definition for a tangent line. So we know the point, right? It's 2 comma 4. So y minus 4 equals my slope times x minus 2. But now I need to find my slope, right? My slope I can find by plugging in x and y into my differential equation, because we know that dy dx represents the slope of the tangent line. So when I plug in 2, I get negative 4 in the numerator. In the denominator, I get 3 plus 16, which is a very ugly answer, but it gives us negative 4 over 19 as my slope. So my tangent line can be defined by negative 4 over 19 times x minus 2. So that is my tangent line, and to approximate the y-coordinate of this point, I can just plug in x equals 3 in for x and solve for y. So I would get y minus 4 is equal to negative 4 over 19 times 3 minus 2, which is 1. So y is equal to 4 minus 4 over 19, which if we were to get a common denominator is 72 over 19, which is our approximation. Now, if I were to actually solve for it, you may not actually be able to solve for an exact value. Yeah, it looks like you can't. They made it to where you would get some radical using the quadratic equation, but this is a pretty solid estimate for the value y on this curve. But yeah, using our differential equation, remember that the differential equation represents slope, and then do our approximation. But not bad for part A, I would say. Very reasonable so far. Most part A's of differential equation questions are. But now let's look at part B. So part B says, is the horizontal line y equals 1 tangent to the curve? Give a reason for your answer. Now, for there to be a horizontal tangent, you know that dy dx would have to equal 0, right? That's just what it is for horizontal tangent lines. Our slope is 0. So at y equals 1, right? That means dy dx. We could solve for our x value by plugging it into the function, but say we don't know our x value. I would get 3 plus 4 times 1, and that would be my derivative. So my denominator is not 0, but looking at my numerator would have to equal 0. So in order for there to be a horizontal tangent line, x would have to equal 0. And we already know that y is equal to 1 at this horizontal tangent. So, it seems like it works, right? When I plug in x equals 0, y equals 1, we get a derivative. It's equal to 0. So boom, we're done, right? Like that should work. But there's kind of one thing that we kind of move past if we just come up with x equals 0 and y equals 1. And that's the fact that this point is not on the curve. In order for this point, 0, 1, to be on the curve, it would have to fulfill that equation, x squared plus 3y plus 2y squared equals 48. Like we would have to be able to plug these in and for this equation to hold. So when I plug it in, I get 0 squared plus 3 times 1, which is 3, plus 2 times 1, which is 2, is equal to 48. That gives me 5 is equal to 48, which is clearly not true. So this point that we found, x equals 0, y equals 1, is not on the curve. So therefore, there is not, or the horizontal line y equals 1 is not tangent to the curve because our x value cannot equal 0 at this point. Another way that you could approach this is by plugging in y equals 1, solving for the x value. I believe it would give you something like the square root of 43 plus or minus. And when you plug that into your derivative, clearly will not equal 0. So you can go either direction and get the correct answer. But if you find a point that's on the curve, the derivative won't equal 0. If you make the derivative equal 0, then our point won't be on our curve. So it just doesn't work out. So that would be our answer to part B. So nice. Halfway through, which is a fantastic place to be. Looking at the rubric real quick, part A was worth 2 points. Part B was also worth 2 points. So we are at 4 out of 9, which is great. 4 out of 9 is a passing score on the Calc AB exam. So, we're halfway done and we're killing it. We're at a 3 already, but I personally would love to be at a 5. So let's keep going. Part C says the curve intersects the positive x-axis at the point root 48, 0. Is the line tangent to the curve at this point vertical? So is the tangent line vertical? Well, we know that when a tangent line is vertical, our derivative, dy dx, is undefined. Because a vertical tangent line, it doesn't have a defined slope. A rise is like infinite, where a run is 0. So, is it undefined at this point? Well, the great thing is we have that expression for our derivative, which represents the slope of the tangent line, right? Negative 2x over 3 plus 4y. So when I plug in this point, it needs to be undefined. That would give me negative 2 root 48 divided by 3 plus 4 times 0, which is just 0. So I get negative 2 root 48 over 3. And that is not equal to 1 over 0 or negative 2 root 48 over 0. It's not undefined, right? So therefore, this tangent line is not vertical because our derivative is defined at the point. It's negative 2 root 48 over 3. So that's our answer to part C. Part C was actually only worth 1 point, which I thought was interesting. So we're moving on to part D. I'm actually heated. I went ahead and I did part D, right? But my phone died in the middle of it and I didn't see it, had no idea. So I have to restart part D. I'm gonna write it all out again. It just ticks me off, right? I gotta do it all over again. Swear it was perfect the first time. We're gonna go back to it again. So imagine this is brand new. Part D, here we go. So it says for time greater than 0, a particle is moving along another curve defined by the definition, or defined by the equation y cubed plus 2xy equals 24. So brand new curve, tossing out everything else. We got this new curve. At the instant the particle is at the point 4, 2, the y-coordinate of the particle's position is decreasing at a rate of 2 units per second. At that instant, what is the rate of change of the x-coordinate of the particle's position with respect to time? So, believe it or not, we have transitioned from a differential equation question to now we're kind of doing a particle motion question. But more than that, we're actually looking at related rates. Because in this function, we have two variables, x and y. They're changing at a certain rate. Tells us that the change in the y-coordinate is 2 units per second. We're looking for the rate of change of the x-coordinate. So let's think about the way we approach related rates. What we do is we get an equation with our two variables, and we take a derivative with respect to time implicitly. So let's take the derivative with respect to time. So on this left side, we would get 3y squared, and then we multiply it by essentially the derivative of our inner function, which is dy dx. So that's the derivative of the first term. This second term, we're going to have to use product rule because we have a function multiplied by a function. So first term times the derivative of the second term, which is dy dt, plus the derivative of the first term, which we could write as 2 dx dt. Gotta remember that the derivative of x in this case is not 1, but dx dt, multiplied by my second term, right? And that will equal the derivative of my right side, which is just 0, because 24 is a constant. So now we can plug some stuff in, right? We know our x value is 4, our y value is 2. So let's start there. 2 squared is 4, so 3 times 4 is 12. We have 12 dy dt plus 2 times x, which is 8 dy dt, plus 2 times dx dt times y, so 2 times 2, 4 dx dt is equal to 0. I'll combine these two terms, get 20 dy dt plus 4 dx dt equals 0. So now we have two variables, which are the rates of change, and one equation. But the beautiful thing is they tell us the rate of change of the y-coordinate, which basically represents our dy dt. And it tells us that it is equal to -2. And we're going to plug it in to this equation. So I get 20 times -2 plus, 4 dx dt is equal to 0. 20 times -2 is -40. Adding that over, I get 4 dx dt is equal to 40, or dx dt equals 10. And my units on that are units per second. But this would be my final answer for the rate of change of the x-coordinate. So part D, really beautiful question. I absolutely love questions that involve multiple kind of aspects of calculus. And this one involving particle motion, related rates, I think is super cool. And I love it. But that is all we got for number 5 of 2024. So only one question left. Hopefully you'll come back for the video for that one. But I hope that you have a fantastic rest of your day and hope to see you soon. Happy practicing. Bye, everybody.